So this is a talk I gave about a year ago now as part of a class we taught with the HMS team on post-wildfire modeling with HMS and RAS. And I think this is the most important talk I give in that class because this is about how to choose those parameters in the non-Newtonian model, in particular the yield and viscosity parameters if you're going to use the Bingham model. This is kind of a work in progress. We are working as an agency and with other partners to really develop what the best parameters are to use for these situations, especially if you're going to model a priori. It's one thing to hindcast these things. It's another thing to try to predict them. And so we've come up with some general guidelines for these models, and this kind of gives us the background for how we came to those guidelines. I would say that right now what we're doing as an agency is we tend to use a viscosity of about 100 Pascal seconds and then bound the possible outcomes with yield strengths of about 700 to 2500. It's what we're doing now, but it's, again, something that's evolving as we do more of this in the agency. But this talk gives you the background for that, as well as some of the nuances to how we think about it. One thing before we jump into it is that a couple of times during the talk, I talk about something we had just done in the class. In the class, this talk follows a laboratory experience where everyone in the class essentially has a race. They make debris flows out of sand, cornstarch, and water, and they race them. Whoever gets closest to 25 seconds wins, and a lot of them just get stuck, and some of them rush down through. It's a pretty instructive laboratory experience, and so I referenced that a couple of times. And so here are some of my thoughts about selecting the non-Newtonian parameters for post-wildfire. Okay, so I had 4 talks. And we had to kind of tell you what the model could do. We had to tell you what the model does, and like the equations. And then I chose to use one of the talks to give you the RAS best practices. And so I have 1 talk left. And I feel like at this point, people are generally like, well, that sounds great. I only have to put in 3 numbers. That's awesome. I don't have any idea what those 3 numbers are. And so that's why I decided to make this last chunk of material about choosing those 3 numbers, or 4 if you decide to do that. Okay, so how to develop these parameters. And so I've got 5 chunks of information. We're going to talk about estimating yield strength, viscosity, the relative impacts of coarse and fine, the sensitivity of these, and then we'll just talk about that Herschel-Bulkley power if you want to use that. All right, here we go. Yield strength. So just for those of you, which is most of you, this is your first time at this material, let's just review what yield strength is. This is Newtonian flow. The slope is the viscosity of water. There's a 0 stress intercept because if you push on water, it'll move immediately. But there's a certain yield strength. There's a stress at which your fluid will stop. The DNFs found that stress. Basically, it progressed to the point where the stress the material was applying was less than the yield stress, so it came to rest. And so that's what we're trying to decide here. And all of these methods need a yield strength. Whether you're using the Bingham, which is what I generally recommend, or if you're using one of these nonlinear equations, they all need this yield stress. It could be 0, but you need to define it. So there are defaults in RAS 6.3.1. The defaults in RAS are what we call the exponential method. I have changed those defaults in 6.4 because I actually want you to have a sense of these numbers, and I want you to type these numbers in. If you just put in these coefficients, you actually have no sense of what the numbers are you put in. But this is the default now, and basically, many investigators have reported an exponential relationship between yield strength and volumetric concentration. And so we have this equation. Yield strength is some coefficient exponential to a power times CV, where CV is in a decimal. 0.5 is 50%. That's not how you put it in RAS, but that's how we use it here. So how sensitive is this to CV? CV's in the frickin' power. It's like, right, like it's gonna bind up. And so this is my fundamental question. Because generally what they do to develop this is they have a lot of kind of low concentration events and then 1 high concentration event. And so their curves look like this. And that looks exponential, but it could also be piecewise linear with a threshold. And so whatever you experience today, you experience that threshold. You either pass through the steep inflection point of the exponential or through some piecewise linear threshold. And so well, this is great. I was going to tell you how to parameterize these equations, and now, instead of one parameter, you switched it out for two. You're welcome. I'm so helpful. Well, how do you do that? Well, there are some established ranges, and these come from Julian's textbook. Pierre Julian from Colorado State, in his textbook, he provides ranges for these. But you'll notice that his equation is not an exponential. It's a 10 to the. It's been a while since I've done logarithmic math. I've YouTubed it. Alex Sanchez and I sat down and we're like, here's what you need to know. In order to turn these numbers, these parameters, into exponentials, you have to multiply them by 2.303, one of the magic numbers in math. So I've changed the RAS documentation. Do not use the Julian parameters. I've converted the Julian parameters for you. And so now, for typical soil, in the range of volumetric concentrations between 65 and 80, we have these parameters give you the range of yield strengths that are about 370 to 5,000, which turns out to be around the range that we're going to recommend. Now, there's some other things going on here. Kaolinite has a bigger range, but for a smaller range of concentrations. It's kind of zeroing in on that threshold. And then bentonite is just bananas. I actually feel like I need to talk about, I need to talk to Dr. Julian about this, because bentonite, if you go to just up to 20%, you're already you're solid, basically. You have the shear strength of a solid, because it's e to the 17. But for 5% bentonite, you can get a yield strength of 200 and get up to like 1,000 with those small numbers. So how do you use these? You choose exponential under yield strength, and you can put your A and your B, and depending on the concentration, you can get anywhere between 375 and 5,000. Now this will be more, or what you can do is just type in, you can compute it yourself and type it in. In future versions of RAS, why might this become more effective?
Concentration changes.
That's right. Right now, you only get one concentration. But if you're using the sediment transport model to route concentration, the concentration changes. Or when we give you a time series of concentration, now your properties can actually change as your concentration changes, which is why this will become a lot more valuable. But now that you only have a single concentration, just choosing a value and going with it makes a lot more sense. And so we could do that, or we could look at the literature and see how have people measured this. Now, one of the big problems with free flow science is that we don't know when these things happen. If you want to study sediment transport, you can go out to the Mississippi River or the Rio Grande tomorrow and measure sediment. Now, you're not going to measure a lot, but chances are in the next 2 years, you're going to get a 50% event, and you can measure that. And over the course of 10 years, you know where to go to measure to get a 10-year event. But we don't know when and where the debris flows are going to happen. And so there are very few direct observations. And this morning notwithstanding, measuring these in the lab is not great, because you can't really simulate large rocks. And we used the cornstarch for clay, but if you scale that, the particle size is like this, right? And so you can't actually scale the cohesives. What you're going to find is that the laboratory data, and the laboratory data is a lot easier to get, but it's also kind of non-representative. So this is one of the famous studies, Cousset and Pugh, and they look at, and they're doing it on a log scale because the belief of that these are exponential. And you can see this is why we kind of think they're exponentials, because they're kind of linear on a log scale. And so kaolinite's weird. These kaolinite values, incidentally, are much higher than Julian's values. But at very low concentrations, you get pretty high shear strengths. But when we kind of look at where the heart of this is, the heart of these, and these are actual soils that they brought into the lab and kind of screened them to get the coarsest particles out, and then did something very similar to what we did. For different water contents, you'll see that between solid concentrations of like 30 and 40%, 30 and 50%, we are between like 80 and 800.
And so this is the meta-analysis that Zhang did. And they plotted, they're looking to see if there's a relationship between yield stress and viscosity, but I like it just because they brought all all these different measurements together, and you can kind of see where they cluster. They cluster between 20 and about 250. All right, so, and this is all in pascals. Now, I've cheated. Gary retired, and so I got away with it. Whether you're an SI or US customary, you're going to put these in SI. You're going to put these in pascals. Pascals is just a better unit, not solely because Blaise Pascal was one of the most brilliant philosophers of all time. If you haven't read Pensées, it's beautiful. I almost named a kid Blaise, and it's kind of a weird post-wildfire name now. But because the Pascal, first of all, I want us all thinking in the same range of numbers. I want us to all come away with this with the idea of what orders of magnitude are we going to define. But the Pascal is such a beautiful number because it takes 1 Pascal of shear stress for water to move a particle 1 millimeter wide, of 1 millimeter diameter. That is super intuitive. 10 pascals, 10 millimeters. 0.1 pascals, 0.1 millimeters. Now I'm playing fast and loose, but within the order of magnitude, it's very intuitive. And so that's one of the reasons I want us thinking about shear stress in pascals. And also, eventually, I just think that all of this work we should be doing in SI because US customary units for concentrations are terrible. All right, so this is the work that I've started to do, is I've started to try to put these in the ternary diagram. And so these are the different investigators that we have. You can see how different investigators, their information clusters in certain parts of the diagram. You can see why I really like Parson for our V&V, because they're the only ones that really explored that debris flow space. And so if I now stratify these by the yield strength that they found, you'll see that we're between 10 and about 500. Blue and gray is low, and it really is, blue is all up here in the very low concentration, hardly hyperconcentrated. There's a lot of gray in the hyperconcentrated fine only zone, and then we start to get above 400 pascals when we get above 50% concentration and we start adding clastics. I promise I'm going to summarize these at the end. I'm going to show you everything, and then we're going to summarize at the end. But I want you to have orders of magnitude in your head. Yes?
What are clastics?
Oh, sorry. Oh, great question. Please do that. Please do that. I've never heard this term before either. But in debris flow, one of the ways that we talk about clay and sand, because sand isn't just sand, it's also rock and gravel and cobbles. Those are clastics, non-cohesives. So I'm going to use that term to mean non-cohesives. And does everyone know the difference between a cobble and a boulder of gravel? Cobble is the size of your fist, boulder is the size of your head. All right, and anything between that is cobble, bigger than your head is a boulder. Philip and Davies also did some of these experiments. Just to answer John's question, this is the very biggest piece of equipment that people have used to do this, and it's not big enough because you can't get anything. The largest particles people have used for these in the lab is 2 millimeters, which that's the sand-gravel boundary. There's no gravel in any of these. But they also did a lit review of everything that had been done at the time. These are observations. Generally, observations are people look at where the debris flow ended up and back calculate what the yield strength must have been. But they are in the 50 to 2400 Pascal range. The median range, about 400 to 1000. And then they make this recommendation that is puzzling to me based on their data. But they actually think that their data are low. And they say, a minimum value of 2000 is suggested, but it could be as high as 3000. And so they're in the 2000 to 3000 range. I actually wrote, that was about midnight last night, sorry about that. All right, I guess kind of getting a little bit of a matrix of numbers in your head. There's a lot of numbers here, but we're kind of in the high tens to low thousands. These are calibrated values. These are values that people use, and this is from Aranto and Franzi. This is mostly Flow 2D. And so I think many of you know that before this was in RAS, the model that was most commonly used to do this was Flow 2D, which was Jim O'Brien's model. O'Brien from the O'Brien method. So it makes a lot of sense that like those were in there very early, but some of this is also customized modeling. What do you notice about these numbers compared to the laboratory numbers? I realize I'm throwing a lot of numbers up here and I'm asking you something, but I also wrote it on the bottom. They're larger, right? These numbers and these numbers are larger than the lab numbers, which is really important. The lab numbers are more precise. A lot of these are pretty estimated, but the modeling and observation numbers are larger. This is, Whipple and Dunn did this study where they did look at multiple runouts, but they looked at it in the Owens Valley, which is about as close to where we are and where some of you are, not the Portland folks, sorry, Seattle, as we can get. And so I thought this one was interesting. They back calculated the shear strength from a number of different debris flows in the Owens Valley. They stratified it actually by runout, but they were in the like 300 to 2100 range. And this is about as close to our setting as we're gonna get. Not post wildfire, but in the kind of western range. This is the only direct observation I found. You gotta be patient to do direct observation with brief light. And also you have to have suspended instrumentation, right? Because nothing will survive on the ground. Jemes and et al., they actually tracked one of these. And they computed dynamic viscosity and yield strength, and they plotted it over time. And so their debris flow had multiple events, but the first one was really like what we really care about. That's gonna be the maximum. And so you can see that they measured between 500 and about 1100 in the front of that, again in pascals. And this debris flow, this is the only one we actually have the velocity for. It's like 2 to 5 meters per second, which doesn't seem like a lot until you realize we're in SI, right? And so that's 6 to 15 feet per second. Getting these up to 15 feet per second is not unusual. Okay, so what have we done? These are the places where we've applied the model, plus Brazil, but it fit on the map. The map would have gotten, the scale would have changed a lot. And Iceland, I guess, but that also didn't put on the map. And what I want you to look at is, because we were applying the Julian parameters incorrectly, we generally didn't use them. Kellie departed from that very early, and I did as well. And so you notice the brown is where we actually tried the Julian parameters, but where are we? Well, this is the debris flow flume. So this is close to prototype scale, but it's not. But for the ones where we didn't use the Julian parameters, we're in the like high hundreds, low thousands. Okay, so what's the takeaway from all that? Well, Julian, 375 to 5,000 for high CVs. That's typical soil, according to Julian. Experimental data, 25 to 400. Way lower than all the other sources. And so I'm putting all this work into pulling together the experimental data. I'm not sure it's that useful at all. Antonio and Franzi, the calibrated values between 200 and 2,000. Philip and Davies, they reported 5 to 2,500. They recommended 2,000 to 3,000. Still curious about that one. Whipple and Zambella, Whipple did the Owens Valley work, but then did a lit review to look at everything everything was available till 1991. They recommended 100 to 6,000. Jemes, who observed that debris flow, 500 to 1,100, and then our experience has been about 600 to 3,000. And so the summary is high hundreds, low thousands, which is why when Kellie ran the model that you guys ran, you guys used the same parameters as she did, because those are about the parameters that I use. Somewhere between 600 and 2,500 can basically bound the experience that we expect. These are very uncertain parameters and very sensitive. But you can see that running both of them, you get a sense of what the possible outcomes are. Okay, do you want more precision? I'm sorry, that's where we are. We're gonna press this some more, but I'm not sure how much closer we can get. Okay, viscosity. So Julian's equation for viscosity is a little bit different. It's essentially the same equation, but there's no A. He just says for everything, the A is going to be 0.001. And so you're only actually dealing with a B. You're only actually dealing with this exponent. He calls it C, we call it capital B. I can't remember why, this is a long time ago. There was a very good reason. Again, many investigators have reported a exponential relationship between viscosity and CV. Is it exponential? I'm dubious. I think it might be a threshold, but it fits an exponential curve really nicely if you only have one really high concentration point. That also could be a threshold. And so same thing. If you want to use Julian's parameters, Julian's equation is 10 to the, and so you have to multiply Julian's coefficients by 2.303. Hopefully, if you don't have Julian's textbook, you never have to think about that again. You just look at the RAS online documentation. What key do you press to get there? F1, you just press F1, and you get to this chart that I put in there Friday. And you can see that for typical soil, the range of viscosities that Julian recommends is about 160 to 2500. Now, in this case, these values seem to be higher than what the literature is showing. But we'll get there. I'm going to do the same thing, I'm just going to do it faster. Okay, experimental data. Well, what's the range that Jean came up with? And so viscosity is, we're still in SI, we're still in pascals, but it's Pascal seconds. Now what you're going to see is that even in SI, there are 6 different ways people report viscosity, and it's all like orders of magnitude. There's like a centipose, not a centipede, a centipose. Centipoise? I don't know. It's like, and it's not like an order of 1,000, like a megapascal. You'll see megapascals. No, a centipose is like 100 or something like that. It's weird. And so what did I do? In 6.4? Because that's annoying, and I got tired of Googling it. I had a calculator in RAS. So whatever you get, you can convert it to Pascal seconds. Because again, I want us all in the same order of magnitude. I want us all in the same unit system so that if you're doing this kind of work and you say, my viscosity is 100, we all know what kind of viscosity you have. So this is these are the like prototype scale, the 2 prototype scales, and so the models were between 2 and 1700, and then Philip and Davies were between 20 and 320. Oh, those are different numbers, aren't they? Those numbers are not the same. And then for Owens Valley and the observed, Owens Valley were between like 30 and 430, and in the observed were between like 20 and 70. All right, if you were able to pull all those numbers together in your head, you have more capacity for numbers in your head than I do. So let's try to see what we just did. Julian, 160 to 2500. This is pretty high concentrations, 60 to 80. Experimental data, 0.2 to 50. It's a lot lower than the other sources. Again, I'm going to say that the experimental data maybe not that useful. And Atronio and Franzi, 2 to 1700. That's pretty good range. I'm not sure that's going to constrain things very much either. Phillips and Davies, 20 to 320. That is surprisingly close to my experience. Whipple and Zambella, 50 to 1,000. Genovis, 20 to 70. Our experience, it was weird. The models I did, based on parameters that I calibrated, the models that Kellie did, the models that other people did in other software, and we just brought those parameters into our software, we all used 100. And so the summary is our experience has been kind of high 10s to low hundreds. Now, this is where you ask the question, does this number make sense? Because if I ask you, does a yield strength of 2,000 make sense? If you ask me, does a yield strength of 2,000 make sense? I don't know yet. But if you ask me, does a viscosity of 4,000 PAS make sense? You should know that, because viscosity is a thing in the world. We all deal with viscous fluids all the time. And so here is viscosity in PA seconds, Pascal seconds on the top, and here are a bunch of different materials that you may or may not have experience with. Mayonnaise is straight up 10. Mustard, a little bit over 100. Ketchup comes in at about 100. And 100 is basically what we generally recommend. How did what we saw outside compare to ketchup? Well, plus or minus ketchup is what I would call what we saw outside. Right? Like, if we dropped 300 milliliters of ketchup, it would depend on the brand. Like, if it's a cheap Save Mart brand, well then, maybe it's less than 100, right? This is the world that I kind of think about, is that I calibrated the model that you're going to work with today with a viscosity of 2,000. the video footage of this event, I'm guessing the volumetric concentration is south of 50. And so is there any universe in which I should be using a viscosity greater than peanut butter? Now, I would say peanut butter is generally the high end. And that is one of the reasons why I really love the Bingham approach, is because it relieves us of equivalence traps, it helps us with parsimony, but also, like, those are fancy words, you can compare it to peanut butter. And so the viscosity is a thing in the world, and it constrains one of your variables. And so now, if you've got 3 wild, unconstrained variables that are very sensitive, you can constrain one of them with physical process, and now you're down to 2. All right, to the lab. So far we've just been talking about the impact of volumetric concentration itself, like how much solid. But solid is not solid, right? There's rock, there's clay, there's plastics, there's debris. And so what is the impact of cohesives versus non-cohesives? Well, again, everything we have here is lab data, and you've already heard you've already seen kind of how lab data stacks up against prototype scale. And so everything that I say you have to take with, okay, a literal grain of sand, right? But there are some conceptual models that come out of the lab that I think are useful. The problem is the conceptual models are opposite. Here's the first one. The first one comes from Socio and Cross. What they did is they took a material, they did different volumetric concentrations, but the volumetric concentration had different percent sands. So it was clay, and at 50% concentration, it's 40% clay and 10% sand, or 30% clay and 20% sand. And so that's the way this works. And so what they found is that, let's start at yield stress because it's easier. The coarser the sand, or the more sand and less clay for the same volumetric concentration, the lower the yield stress was. The yield strength dropped as you added sand. Viscosity is more complicated. For viscosity, at first, if you add like 10% sand, the viscosity actually increases, and then it decreases the more sand you add. Okay, so that's what the lab says. And there are at least 2 studies that show this. This is where Richard Iverson's critique comes in. Richard Iverson, I again said, kind of the GOAT of experimental debris flow, and he has a couple of beefs. One of his beefs is that we shouldn't be doing rheology at all, and you should know that. You should know that the top debris flow scientist thinks that rheology is inappropriate. I would say, I believe in heuristics. When I'm modeling reality, I believe in switching out an impossible question for an easier question, and then answering the easier question to get part of the way there. The laboratory scale doesn't work because you can't scale the cohesives down far enough. And so what we have out there is actually scaled gravel that has interparticle forces, that has interparticle charge. And so it's not realistic at all to scale up to what we do. And that's why Dr. Iverson built that giant flume. But Dr. Iverson starts from the other side. He says, are these events usually mostly cohesive? No. These events are usually, his definition of a debris flow is a huge diversity of particles. From clay to, we should have a term that's bigger than boulders. Once it's bigger than your car, it should be called something else. And so what is the volumetric concentration of fines in most of these debris flows? Well, it's usually less than 20%. So he doesn't start here and add solids and clastics. He starts with clastics and adds fines. And here's what he found. So in the video that I provided before the class, we showed this video with him explaining it, which is going to be better than me explaining it. But so go and watch that. But here they ran the debris flow flume. These are 2 debris flows, and one of them has 2% cohesives, and the other has 20% cohesives. So it's 20% on the right, 2% on the left. Which one do you think is going to go farther and faster? 2% farther and faster? Who says 20? Okay, we're going to get another view. Now they're going to switch unhelpfully, which is why I couldn't label them. Now, this is the 20, and this is the 2. So the 20 is on the right. And so this is, I think, one of Iverson's huge findings, is that if you actually think about debris flows the way they actually are, mostly clastic, a huge diversity of material that probably has less than 20% fines, the more fines you have, the faster and farther your debris flow goes because the fines are part of the fluid phase. It makes the fluid phase more viscous, and so it maintains that internal pore water pressure, essentially hydroplanes. But do we just care about the viscosity of the fluid phase? No, if we're doing what we call single phase modeling, his model looks at the fluid phase and the solid phase independently. We don't do that. We just call it all one mixture, and so we need a viscosity that accounts for all of that. And so in general, the idea is that for real debris flows, the higher the clay concentration, up to about 20%, the faster it goes. And so in the podcast, I told them the first time that I heard that finding, I didn't actually believe it, because I thought the more cohesives you add, the stickier it'll get. And he says, maybe that happens at 50%, but he never tested 50% because that's not generally what these materials, the way these materials unfold. So the moral of the story is that in general, in the real world, the more cohesives you add, the faster and farther it goes, up to about 20%. Okay, sensitivity. You'll notice that in the first model that we just watched, the second workshop is going to be more freeform. We're just going to have you choose these things. But when we asked you to do this, we gave you a range because we should always do sensitivity on uncertain parameters. And again, we're kind of new at this, so this is what I believe now, and we may update this as we go. But here is a simulation where I'm running. The yield strength is set at 700, but I'm running viscosity between 0 and 10,000. All right? Think about what you would expect. If I had more time, I'd have you formally develop hypotheses, but I do not. Did that do what you thought it would do? What did it affect and what didn't it affect?
Velocity.
What's that?
Velocity and extent.
Okay, it affected velocity. Travel time, warning time, those were all affected. But is your floodplain extent substantially different? It is not. Your depth is going to be different because if it gets there slower, if the same volume gets there slower, the depth is going to be higher. And so, while it was channelized, it's going to be deeper, but that doesn't really turn into area. But the extent is about the same. It just takes longer to get there. Okay, so if you look here, if you look at essentially the mud hydrographs in the channel, when it's all kind of channelized, it looks the same. The mapping looks the same, but the depth, the higher viscosity materials are much, we're looking at a difference between like 3 feet and 8 feet. And so if you have one of these nice homes like on the valley, that could be a huge difference. But down in the plain, the terminal depth is pretty similar. It's just different of how long does it take to get there, to the order of 30 minutes to an hour. I would argue that once you kind of take some time staring at that chart and understand the different physical viscosities in reference to things that you know, that's actually going to become more intuitive than n value, particularly mountainous ephemeral n value. What's the n value of that? I've been doing this for 25 years and I can't tell you a priori. It's like, I don't know, 0.18 to 0.35. What's the viscosity of that? It's It's probably 100 to 200. And so I do think that, I actually do think that the more we do this, the more comfortable we're going to feel with viscosity. But the other thing is that which is more stable? Adding viscosity or adding n value? N value, because n value is static. Viscosity is tied up with that self-referential term, which can add instability. So you might get in a situation where you can't get the model stable, and so instead of increasing viscosity, you increase n value. And that's just what we do. I'm not gonna n value shame you. Well, if you use a 0.8, I might, but I won't put it on Twitter. Okay, so here, I will show you in a little bit. If you use the exponential form where viscosity is a function of volumetric concentration, weird things begin to happen. Because you increase the concentration and your floodplain gets bigger, you increase it more, your floodplain gets smaller. And I'll show you why in a minute. But yeah, but here I'm just trying to keep everything the same so we can just look at the sensitivity of one parameter. Okay, so develop your hypothesis. Viscosity at 500, but we're going to change the yield strength. And n value stays the same thing. So these are traveling at pretty similar speeds at the beginning, but the number of people who are affected is pretty substantially different. The area of the mud plain is substantially different. And so you could be in a situation, if you're using the exponential form for yield strength, and you increase your volumetric concentration, you could be saying, oh, I'm making this thing worse. I'm going to be conservative and put a lot of volumetric, put my concentration at 70, and that's going to bulk my flow huge. But what's this also going to do? It's going to increase your yield strength, and it's going to stop it from moving. And so if your volumetric concentration is actually 50, you could have less total volume, but more people will be impacted because it'll get to them. You have a fixed storm, but when you add concentration to a fixed amount of water, you do two things. You add the total volume, which will increase inundation, but you also increase the viscosity and the yield strength, which will decrease velocity and actually decrease inundation. And so it's a very complicated idea. This constrains the uncertainty, but what is the range that we probably believe in? Well, we probably believe in these three colors, right? And actually, that's a pretty constrained uncertainty, right? That's like plus or minus 10 families. And so, I mean, this is not super populated, but we saw yesterday sometimes these places aren't. So yeah, but one of my, I used to say this one way and then someone quoted it wrong, and so the thing I used to say is, if you only give one answer in sediment transport, it's a lie. Because you should give multiple answers. And then we were at RARD once, there were like 150 people in the room, and someone stood up and said, Stanford Gibson says all sediment modeling's a lie. I was like, maybe I should not say that anymore. But I do believe it. Like, you should always give multiple answers when you have this many uncertain parameters. One of the things we haven't touched at all in this class, partially because we haven't done it much in practice, is yield strength is fundamentally geotechnical. And so what Ian's talking about, the cross model, but also the Coulomb model and the Volamy model, which I just said those words, I didn't even define them, is the idea of let's use geotechnics to make the yield strength physical. And that we have those in RAS right now, but we're not using them a lot. And the idea is that it would be nice to get, because viscosity is intuitive, volumetric concentration is hard, but it's intuitive. It'd be nice to get yield strength more scientific, essentially. Okay, so in general, yield strength affects runout and inundation. Increased yield can, and then increased yield can actually decrease runtime. Why? You have fewer active nodes, fewer cells are running. And so you might find you increase the yield and your runtime halves. You're like, what's going on? Well, you're not using as much computational power because fewer of your cells are wet. And then in general, viscosity increases the depth, decreases the velocity, so it decreases the arrival time, increases, you can work that out. And generally, increasing the viscosity makes things less stable because of that weird feedback on that term. This is not universal. I've not seen this in all of the models, but in this classic alluvial fan runout model that we're doing, this holds. If your model is all channelized, it's going to be a little bit different because yield actually doesn't totally run out. But we can talk about that another time. Okay, finally. After all of that, after we've kind of talked through kind of how you would constrain within an order of magnitude these three uncertain parameters, I'm kind of curious what kind of person would want to add another one. But if you are, again, Herschel-Bulkley is used primarily for the lab, where people have very detailed data, but we know what we believe about the lab, what I believe about the lab. But it gives you the opportunity to have these nonlinear rheological models, which at some point we might believe. Right now, I don't believe that a nonlinear rheological model is going to give us a better answer a priori. It might give us a better answer in hindcasting, but I don't believe one of these will give us a better answer a priori. In 3 years, I might believe something different about that. So I reserve the right to be skeptical. But just as a reminder, if your n value, this is a different n, if the power of your strain term is greater than 1, then you are dilatant, shear thickening. You have the same properties as the cornstarch, right? The more you stress it, the stronger it gets. And if it's less than 1, you're pseudoplastic. You have shear thinning. It's thinning. That's awesome. Shear thinning. I'm almost done talking. The more you stress it, the weaker it gets. Well, thinning is the right answer for cohesives. And so again, we've got this. This is again part of the lit review that I'm trying to put together for you all. But this is again our ternary diagram. Again, the same lab experiments. And what you'll find is, so the n value, the light blue is less than 0.5. This is seriously shear thinning. Anything blue is shear thinning. I've made the Bingham range plus or minus 0.15. All right, and that's gray. And then red is thickening, and bright red is really thickening. And you'll notice that thinning is much more common than thickening in the lab. And but why is that? Where's the thinning? Well, the thinning is along this axis, which means how many clastics did they have? 0. This is the zero clastic axis. And so in the cohesive only laboratory experiments, we're strongly shear thinning. N values, these powers are like 0.3 to 0.5. But how representative is that of our materials? Not a lot. And where do we see most of the shear thickening? Well, most of the shear thickening is, this is all pretty high volume material, but it's when you're starting to get into the clastic range. In the clastic range, you start to get powers greater than 1.5, and you start to get some shear thickening. And so in the lab, there are enough data that we actually are starting to see some trends. One of the big questions is that remotely transferable to the field? I don't believe it yet. I may be convinced the more field data we get. But for now, my recommendation is stick with Bingham. 3 parameters is hard enough. If your least certain parameter ranges from 800 to 2500, you don't need to get that cute with the math because it's already bounded in that uncertainty.